In this class, we will going to study the analysis of transistor amplifier circuit using H parameters. In the previous class, we have studied the hybrid, that is H parameter model for C configuration, and also the H parameter model for CB and CC configurations. So the transistor model is nothing but its equivalent, electrical equivalent circuit. So when the transistor is replaced with its electrical equivalent circuit, we can do some mathematical analysis on the amplifier circuits. So in this class, we are going to study the analysis of transistor amplifier circuit using H parameters. So the transistor here, in the analysis, we will replace the transistor with its equivalent circuit or equivalent H parameter model in the analysis. Here the transistor amplifier is constructed by connecting here at the input side voltage source is connected, and at the output side a load impedance is connected to the transistor amplifier. A source with internal resistance Rs at the input side and a load having impedance ZL on the output side is connected to the amplifier, basic amplifier circuit. Here the transistor, now to do analysis, the transistor is replaced with its equivalent H parameter model. Here I1, V1 are the input current and voltage of transistor, and I2, V2 are the output current and voltage of a transistor amplifier. Vs is the input source voltage with internal resistance Rs, and ZL is the load impedance, and IL is the load current. Now to do analysis, this transistor is replaced with its equivalent H parameter model. So at the input side we have input equivalent circuit of H parameter model, that is HI, V1 and HR, V2. That is the input voltage is represented with these two parameters, and at the output side we have a current source with a admittance, parallel admittance H0. So let us first, the parameter of the amplifier is the current gain. We will find the current gain of the amplifier. To find the current gain, you know the definition of current gain, that is the output current to the input current. The load, here the output current is the load current, and the input current is I1. So the current gain or current amplification is represented with AI, where capital A indicates the gain and I is the current. AI is the current gain, is the ratio of IL by I1, and that we can write IL by I1. IL is the load current, output current, and I1 is the input current. IL we can replace with minus I2 because the IL is flowing into the load and I2 is flowing into the transistor. IL is opposite to the I2, so therefore IL is replaced with minus I2 by I1. But from the H parameter model of the transistor, we can write the equation for I2 that is I2 is equal to HF I1 plus H0 V2, and all by writing the equation in terms of I2, replacing the voltage V2, that is V2, that is the output voltage V2 is ILZL, product of IL into ZL is V2, that is nothing but equal to IL is again replaced with minus I2, so V2 is equal to minus I2 into ZL. Substituting V2, that is minus I2 ZL. Now rewriting the equation I2, the equation of I2 we can rewrite the equation I2, that is I2 is equal to HF I1 minus I2 ZL H0, taking I2 as common, I2 plus I2 ZL H0 is equal to HF I1, taking I2 common, I2 into 1 plus H0 ZL is equal to HF I1. Now we can write the equation for current gain AI, which is the ratio of I2 minus I2 by I1. So minus I2 by I1 is equal to minus HF by 1 plus HO into ZL. So it is the equation of current gain, that is current gain AI is equal to minus HF by 1 plus HO into ZL. This is the equation of current gain of the transistor AI. AI is equal to minus HF by 1 plus HO into ZL. It is the equation of current gain. Now another important parameter is the input impedance of the transistor, that is Zi. Here RS is the signal source internal resistance. The input impedance seen when looking into the amplifier terminals 1, 1 at the input of the amplifier. It is the ratio of input voltage to the input current, input impedance Zi, V1 by I1, and we know the equation for V1, input voltage V1 is equal to HI I1 plus HR V2. V1 is equal to HI I1 plus HR V2. Substituting V1, HI I1 plus HR V2 divided by I1. Substituting the value of V2 is equal to minus I2 ZL so HI I1 plus HR V2 by I1 separating the denominator. So hi I1 by I1 gets cancelled, hi plus hr v2 by I1, and substituting again v2 value. V2 is minus I2 ZL, that is Zi we can write Zi is equal to hi plus minus h, and v2 is minus I2 ZL, and I2 again we can write minus I2 as AI into I1. From the equation of current gain, we have AI is equal to minus I2 by I1. From this we can write equation of I2, that is I2 is equal to minus I2 is equal to AI into I1. So equation V2 is AI into I1 ZL. Substituting V2 and writing the equation for input impedance Zi is hi plus hr, V2 is AI I1 ZL by I1 after simplification I1 gets cancelled. Now we can write the equation for impedance Zi. Input impedance Zi is equal to hi plus hr AI ZL. And substituting again the value of AI in the above equation, Zi equal to hi minus hf divided by 1 plus ho into ZL. It is the equation of current gain AI, and hr ZL divided hr ZL. So the input impedance Zi is equal to hi minus hr hf ZL, and taking ZL common in the denominator, and 1 by ZL plus H0, and ZL removes, gets cancelled in the numerator and denominator, and can write the equation, simplified equation for the input impedance Zi equal to hi minus hr hf divided by H0 plus 1 by ZL, or YL plus H0. So this is the final expression for the input impedance of a basic transistor amplifier circuit. Coming to another important parameter of the transistor amplifier is voltage gain, that is represented with the AV, capital A subscript V, AV. The ratio of output voltage V2 to the input voltage V1 is known as the voltage gain of the transistor, that is AV is equal to V2 by V1, and V2 we have V2 is equal to minus I2 ZL, and I2 again minus I2 we can write AI into I1 ZL. Substituting V2, that is A1 AI I1 ZL divided by V1, AI I1 by V1. So taking I1 into the denominator side and rewriting the equation for voltage gain AV. AV is equal to AI into ZL divided by ZI. So voltage gain is represented with the product of current gain into load impedance by input impedance. That is AV is equal to AI into voltage gain. AV is represented with current product of current gain into load impedance by input impedance ZI. The output impedance output admittance Y0 is output admittance. Y0 is the ratio of I0 by V0, output current to the output voltage, by setting Vs to 0 by finding the output admittance. Because it is the admittance that depends on the conductance, so we need to keep the source voltage to 0, because otherwise the admittance gets changed, because the transistor is a current operating device. So the input change in input conductance may change the output conductance. So output conductance depends on the output current depends on the input current. So to avoid this, reducing the source to 0, and taking ZL to infinite and making ZL to infinite by driving the output terminals from the generator's side. And then we can write the equation for the Y0. Y0 is equal to I2 by V2. With Vs is equal to 0 and RL is infinite. And we have the equation for I2 from the H parameter model. I2 is HF I1 plus H0 V2, dividing on both sides with V2. I2 by V2 is equal to HF I1 by V2 plus H0 applying KVL to the input circuit with source voltage 0, RS I1 plus HI I1 plus HR V2 is equal to 0. Taking I1 common, RS plus HI into I1 plus HR V2 is equal to 0. RS plus HI into I1 plus HR V2 I2 by V2 is equal to hf I1 by V2 plus H naught. The output admittance I2 by V2 So writing the equation for I1, which is minus HR V2 by RS HI, RS plus HI. Here in the output admittance we have the equation I2 by V2 is equal to HF I1 divided by V2 plus H naught. In this equation, replacing the value of I1 by V2, I1 by V2, I1 by V2 is equal to from this equation, from the equation RS plus HI, applying KVL to the input circuit, we have the equation RS I1 plus HI I1 plus HR V2 is equal to 0 from the input circuit. From this equation we can write the ratio of I1 by V2, the ratio of I1 by V2. From this we can write I1 by V2 is equal to minus HR divided by RS plus HI. Substituting this ratio I1 by V2 in the equation 1, then in the equation 1, that is I2 by V2 is equal to minus HR by RS plus HI. In this equation, I2 by V2 is equal to HF I1 by V2 plus H naught, but I1 by V2 is minus HR by RS plus HI. Therefore I2 by V2 is equal to minus HR minus HF divided by RS plus HI plus H0. So rearranging the equation, I2 by V2 is Y0. Y0 is equal to H0 minus HF divided by RS plus HI. This is the final equation for output admittance. That is Y0 is equal to H0 minus HF divided by RS plus HI. Similarly, voltage amplification factor, taking the source resistance into account. In the previous expression, we have calculated the voltage gain without considering the source resistance. But considering the source resistance, the voltage gain is given by the expression AVS. AVS is equal to AVS, voltage gain with source resistance, is defined as the ratio of V2 by Vs. V2 is the output voltage, overall output voltage, and Vs is the voltage coming from the source. So V2 by Vs, we can this equation we can write V2 by V1 and V1 by Vs. V2 by V1 into V1 by Vs. But V2 by V1 we can write AV, and V1 by Vs we have to find the ratio V1 by Vs. From the equivalent input circuit using Thevenin's theorem, Thevenin's equivalent circuit, we can write the equation for V1. V1 is equal to, V1 is the voltage across Zi. So therefore V1 is equal to Vs by Rs plus Zi into Is. V1 is equal to, this is the voltage and these are the two total resistance. So V1 is equal to the Is into, actually V1 is equal to Is into Zi, but Is is, we can write the equation for the current Is is Vs by Rs plus Zi. Substituting Is in the equation V1, so V1 is equal to Is Zi, Is is Vs by Rs plus Zi, Vs divided by Zi plus Rs into Zi. Rearranging the equation, V1 by Vs is equal to Zi by Zi plus Rs. The ratio of V1 by Vs is given by Zi by Zi plus Rs. So therefore, from equation, let us call it as equation 1 and this as equation 2, V1 by Vs as equation 2. We can write the voltage gain with source resistance AVS is equal to AV into V1 by Vs, but V1 by Vs is equal to Zi by Zi plus Rs. So therefore AVS is equal to AV into Zi by Zi plus Rs. Substituting the value of AV is equal to A into ZL by Zi. In the equation 3, let us consider this as equation 3, AV into Zi by Zi plus Rs as equation 3, and we have the equation for AV AV is equal to A into ZL by ZI. Substituting AV, so A into ZL by ZI plus RS. A into ZL by ZI, and ZI gets cancelled. A into ZL divided by RS plus ZI. AI into ZL dividing the numerator and multiplying the numerator and denominator with RS. AI into ZL into RS divided by ZI plus RS so current amplification factor here AIS is equal to AI into current amplification factor AIS is equal to AI into RS by RS plus ZI. Current amplification factor here the current amplification factor AIS, current gain with source resistance, is AI into RS by RS plus ZI. AI into RS by RS plus ZI we can write as AIS, so therefore AVS is equal to AIS into ZL by RS. This is the equation for the voltage gain with source resistance. The final equation for voltage gain with source resistance is AIS into ZL by RS. Current amplification factor taking into source resistance into account by considering the source resistance, applying Norton's equivalent circuit, taking the Norton equivalent input circuit. Overall current gain AIS is the ratio of minus I2 by IS, and this we can write as I2 by I1 into I1 by IS, but I2 by I1 is AI, therefore AIS is equal to AI into I2 by I1, AIS is equal to AI into I1 by IS. Now we need to find the ratio. To find the equation for AIS, we need to find the ratio I1 by IS. Here I1 by IS is I1 by IS so from the Norton's equivalent circuit we can write the equation for I1. I1 is equal to total current IS into RS by the total resistance RS plus ZI using current division rule. From that, rearranging the equation, I1 by IS is equal to RS by RS plus ZI. Substituting the ratio I1 by IS in the equation AIS, so AIS is equal to AI into RS by RS plus ZI. This is the equation of current gain by considering the source resistance AIS. So therefore AIS, overall current gain with source resistance, is given by the equation AIS is equal to AI, the current gain, into source resistance divided by RS plus ZI. And coming to the power gain, operating power gain AP, it is the product of voltage gain and current gain. AP is equal to ratio of P2 by P1, but P2 is the output power and P1 is the input power. P2 is minus V2 I2 and P1 is I1 V1. Here V2 by V1 we can write as AV, and I2 by I1 we can write as AI. So AV into AI. AP is the product of voltage gain and current gain. Power gain is the product of voltage gain and current gain. But the voltage gain we can write the equation for voltage gain as current gain into load resistance by input resistance. So the voltage gain replacing AV with AI into ZL by ZI. So AI square into ZL by ZI is the power gain. Equation of power gain in terms of current gain. So this is the expression for power gain. So far we have derived the equations for current gain. AI is equal to minus HF divided by 1 plus HO into ZL, and voltage gain AV is equal to AI into ZL by ZI, where AI is the current gain, ZL is the load impedance, and ZI is the input impedance. And the equation of input impedance is ZI is equal to HI plus HR into AI ZL, or we can write ZI is equal to HI minus HR HF divided by 1 plus HO into YL, and the voltage gain with source resistance is AV into ZI divided by ZI plus RS, or AA into ZL by ZI plus RS in terms of current gain, voltage gain with source resistance. In terms of current gain, AA into ZL by ZI plus RS, or AA into ZL by RS. Output admittance Y0 is equal to H0 minus HR HF divided by RS plus HI is equal to 1 by Z0, and the overall current gain AIS is equal to AI into RS divided by RS plus ZI. So these are the equations of the different basic transistor amplifier parameters: voltage gain, current gain, input impedance, output impedance, current gain with source resistance RS, and voltage gain with source resistance, and power gain of the basic transistor amplifier circuit. approximate model. So actually this is the transistor H parameter accurate model. So we can simplify this hybrid model, H parameter model of the transistor, simplified model, hybrid model. In the simplified hybrid model, HRE and HO is very small and they can be neglected. HRE we see value is very small comparing with HIE, and HOE we see value is very small comparing with HFEIB. So in the output circuit we can neglect HOE, and in the input circuit we can neglect HFEIB, so that the simplified model of H parameter model for CE configuration. This is the CE configuration, simplified hybrid model for CE configuration. Here we have only one parameter HIE in the input side and one parameter HFEIB on the output side. So this is a generalized simplified equivalent circuit from which we can construct any transistor model, simplified model for all the three transistor configurations, making this terminal common, between these two. This is the common between these two, and this will become common emitter configuration. Similarly, common base configuration, base is common between the input and output. So this is the common base, this is the input side, this is the output side for common base configuration. Similarly, common collector configuration, base acts as the input, this is the input side and this is the output side. So using generalized simplified equivalent circuit for all the three transistor configuration, from the simplified model of C transistor, we can write the current gain equation for current gain. AI is the ratio of I naught by IB. But I naught is nothing but HFE IB by IB, so it is simply HFE. And RI, it is the V1 by IB, VI by IB. VI is HFE, HIE into IB by IB, so HIE. Voltage gain is the ratio of V0 by VI. V0 is I naught into RL. VI is HFE IB, HIE IB. So I naught by IB is AI. AI into RL by HIE. AI is minus HFE, substituting minus HFE into RL by HIE. R naught, output resistance, the ratio of V naught by VI, V by I, where RL is infinite, Vs is 0. R0 is infinite. So simply for common base configuration, base is common. Between the input emitter and the output collector. So for common base configuration, the hybrid model, the parameters, calculation of parameters in terms of CE, common base configuration. So here the common base configuration using simplified hybrid model. The base is acting as common. This is the base terminal acting as common, and the emitter terminal is the input, collector is the output terminal. So the ratio current gain for CV configuration, I0 by IE, input current is IE, I0 is HFE, I0 is minus of HFE IB, and I0 is minus HFE IB, and input current IE is equal to 1 plus HFE into IB. So IB gets cancelled. Here we can write the equation for I0. I0 is equal to minus HFE IB divided by IE is IC plus IB, but IC is HFE IB. So taking IB as common, taking IB common, 1 plus HFE IB cancelled. So HFE by 1 plus HFE is the equation for the current gain. Similarly, the input resistance is the ratio of VI by IE. We know the equation of II is IB into 1 plus HFE, and VI input voltage is HIE into IB. So HIE by 1 plus HFE. Input impedance, voltage gain V0 by VI, HFE IB minus HFE IB into RL divided by HIE IB. So therefore it is HFE into RL by HIE. So the parameters of H parameters of CB configuration in terms of CE H parameter model. Similarly, we can write the equation for CC, common collector configuration, in using the CH parameter model. CC H parameters for CC configuration, value here, collector is common, using the H parameter model of CE transistor. See, we can do analysis for common collector configuration. In the common collector configuration, base acts as input and emitter is the output terminal. So the current gain is the ratio of I0 by IB, IE by IB, but IE is minus of IB into 1 plus HFE, IB HFE IB, 1 plus HFE IB divided by IB, so it is 1 plus HFE. Input resistance Ri is the ratio of Vi by IB, but Vi applying KVL to the input side, Vi, so HFE IB plus IE into RL, IE into RL, because we have a current source in the input side, it acts as open, so IE into RL, but IE is 1 plus HFE into IB, taking IB common, HIE plus 1 plus HFE into RL, equation of Ri. Similarly, the voltage gain, ratio of V0 by Vi, I0 into RL divided by IB into Ri. So I0 by IB is AI, current gain, into load resistance by input resistance. AI is 1 plus HFE and Ri is HIE plus 1 plus HFE into RL. So these are the equations for CC amplifier in terms of CH parameter model. CC configuration equations, and these are the equations of CB in terms of CE, and this is the comparison table of H parameter for CE, CB and CC configuration using simplified H parameter model of transistor. For the parameters, current gain, input resistance, voltage gain, output resistance. This is a comparison table of H parameters in terms of C model. So we will stop here today class. In this class we have studied the H parameter simplified transistor amplifier analysis. We have derived the equations for current gain, input impedance, voltage gain, output impedance, voltage gain with source resistance, current gain with source resistance, power gain using the transistor H parameter model in C configuration, and later using the simplified H parameter model for C transistor. We have calculated the same parameters for CB and CC configuration, and also the comparison table of H parameters of CB CC configurations in terms of CE H parameters.